You know, sometimes I wonder if it's Bruno Mars teaching this class, what the class would look like. I was thinking about how can I rap like Bruno Mars for the course content, but unfortunately I just figured out that I can't do it. So, but you know, even though I cannot do it, you have no choice to listen to what I'm lecturing today, and I think it's really important because that's actually a big part of this class, dynamic instruction scheduling, and we said the philosophy behind dynamic instruction scheduling is that we're already aware that whenever an instruction has all its input ready, whenever there is a functional unit ready, whenever I'm done with what I need to do in the current stage, there's no reason why I cannot advance. So in this way, we try to design hardware that executes your instruction follow this philosophy. And the first one we saw is the Thomas-Law algorithm. And the Thomas-Law algorithm, the basic idea is that we redirect all the outputs to a reservation station. So instead of your value depending on the name, you have your instruction depending on the outcome of a reservation station. So even though there are then aliases like right after right or read after write, write after read, you will not be affected by those. However, Thomas-Law algorithm is severely constrained by the number of reservation stations associated with each pipeline unit. So we want to have more flexibility over there. So most of the modern processors, like the two papers that we assigned in the class, we implemented so-called register renaming logic. The basic idea of register renaming logic is still similar to the Thomas-Law algorithm in a way that we just redirect all the outputs to so-called physical registers. And by having your instructions depending on those physical registers instead of those virtualized architectural registers, we can decouple those name aliases or say false dependencies. So in this way, as you can see, because we don't have the and if you have sufficient amount of physical registers, you can get rid of the constraint of limited number of registers in each functional unit. So for the same pieces of a code, we can take less cycles, fewer cycles to issue all instructions. And however, people are greedy and we are never satisfied. And we figure out that even though we are able to rename all the instruction output to physical registers, but we still have issues of filling our functional units. Looking at this diagram, most of the time you are just using one or two of them. So is there a way we can try to fill those functional units? So it turns out that the reason why you cannot fill them is because you have limited amount of choices. So what you could do is that what if we widen the front end of your pipeline in a way that we fetch more and decode more? So the pipeline, so this technique, or say this kind of process design, is called Superscalar. So you can consider that your processor now has a front end which keeps fetching, decoding, and renaming instructions and put them in the instruction queue. And there is a back end which your front end tries to fill as many instructions as possible and to the back end. So the front end is like the supply, and the back end is a very hungry monster that give me instructions, I want instructions. And so that's the basic idea of the scalar pipeline. And so that's walk through this example in extending the front end of the register renaming pipeline. So if we have the two, so here we have a new term called issue list. And to issue means that this processor has the capability of renaming and putting two instructions into execution at each cycle. So for this two issue pipeline, we can assume that the processor has the capability of renaming two instructions at the same time, and of course, and then after you rename, those instructions can be put in the issue queue. By putting them in the issue queue, meaning that they are renamed, and all they need to do is wait for available functional units. And for these two these instructions, as you can tell, well, the load instruction that will go to the memory pipeline, the add instruction will go to the integer pipeline, and there is no values there. Well, actually, there is a slight dependency between the first and the second instruction. So you can imagine is that the first instruction after rename, it can execute, but the second instruction has to wait. So the next cycle, so that's what happens here.
And in the next cycle, again, this 2 gets renamed. And as you can tell, after rename, the store instruction depends on P2, which is the outcome of the second instruction. So we cannot issue this one in the next cycle. However, if you look at the rename add immediate instruction, it's not depending on any physical register. So it can directly go to execution in the next cycle. So then here you see this instruction go to the integer pipeline because it doesn't have to wait and all its value is ready. And in the meantime, we keep renaming instructions like 7 and 8. And if you look at the dependency chain of them, you will figure out that for this branch instruction, it will be able to execute after the add instruction finishes execution. And however, there is still a dependency chain between 6, 7, and 8. So then let's keep going. And so for this cycle, as you can tell, because this instruction hasn't finished its write back state yet, so the branch instruction cannot be executed. However, you can imagine that the next cycle, this value will be broadcast out, and the branch instruction would receive that, and it can get the value. And the same here for the memory instruction, because it hasn't been written back. So the instruction like this 2 and 3 that has dependency that is waiting for this one to continue cannot be executed at the same time. However, you see there is an out of order execution here, like this fourth instruction, it gets executed way earlier than other instructions. So again, here as we said, well, since this one gets returned back, we can have the fifth instruction go to execution. And for this sixth instruction, because it's also depending on the value of P3 generated by force. And this is a 2-issue pipeline, so we have no trouble putting both of them into their execution. So in this way, you can see, well, here, this 2 instruction gets executed even earlier than this 2, right? And now the next cycle, because this one gets returned back. So finally, this instruction can be executed. However, the third one, the third instruction is depending on, it's depending on the value of P2, which is the outcome of the second instruction, so it cannot get executed. And if you run through this example for the same philosophy, you will figure out that if you want all instructions to be issued, it takes only 10 cycles, which is 2 cycles fewer than the previous example. And on the other hand, thinking about this, right? If your backend pipeline is busy enough, and if we have sufficient amount of instructions like this, if we keep going on, and if this sequence of instructions takes 10 cycles, it means that if you have this kind of code going on and going on, it's every 10 cycles, 10 instructions, so you can think the average CPI of this pieces of code will be 1 for this particular pipeline. Okay, so that's where we are at now. But the thing is, are we okay with this pipeline? Is this pipeline having no trouble? That's the topic we are going to talk about today. However, there is also a very interesting example that we have been talking about. So I want you to rethink, try to relate the code example we have in the class to the current out-of-order issue processor and see the rationale behind these 2 pieces of code. So let's go through this example, walk through this example by yourself. And as you remember, you don't have to draw the pipeline diagram. You can use the data flow graph and see for this one, assuming that the memory instruction, it still have to go through, or say like the outcome of the memory instruction will be 4 cycles after the 4th cycle. It will be available for other instruction, and for ALU instruction it will be 2 cycles. And if you use this number, can you tell me how many cycles it takes to empty the issue queue of this? If we have this 7 instructions in the instruction queue right now. Yes, question.
I'm confused. So it's
okay, this is not using Excel. This is using the regular. Is that the question?
yeah.
Okay. All right.
Let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay. Okay, most of you think it's C. Well, not most of you, about half. So what if you discuss with your friends and see if you can convince each other that you are right?
Yeah. Three have the point of the dog. Depending on three, but if I choose that go here. Five. And six. It is four. I think it's an average for cycle. We can do the second. Have to have these words.
All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now more of you think it's C, but make sure that's not the result that we just follow the majority. So we still have to go through this question. So again, right, if we want to use the way that of data flow analysis for this pieces of code, right, and assuming that this is a processor with 2 fetch and issue with. So we can assuming that for the first cycle, we are going to fetch 2 instructions, 1 and 2. However, here, there's one thing. We only have 1 memory pipeline. So if we have 2 memory instructions,
they have to go into the memory pipeline in order. So in the first cycle, although we get both 1 and 2, however, only one of them gets into the pipeline. So only the first instruction gets into the pipeline. However, remember, because we pipeline each stage in a memory pipeline, so the next cycle, once the address resolution is freed, the second instruction can go in, right? So because of that, even though the next cycle we fetch instruction 3, however, the earliest point that instruction 3 can get executed is only when the first instruction finishes. So it will be 4 cycles later. So that's why you can only issue the third instruction after 4 cycles after the first instruction. And for the fourth instruction, which is this one, after renaming, you can imagine that this instruction only depends on the value of x7. So it will also be available 4 cycles later after the second instruction. So it will be here, right? And now looking at the fifth instruction, it's depending on the value of 3. So it will be available 2 cycles after the third instruction. So you can put it here. And again, for the sixth instruction, it's depending on the outcome of the fourth instruction. So it will be available here. And for the seventh instruction, it's depending on the outcome of the fifth. So it will be available here. So if you look at this, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so you guys got it right. It's indeed 9 cycles to issue the 7 instructions. And one thing that if you look at the data flow graph, right, this sequence of instruction is perfectly divided into 2 data flow, two small data flow graphs. So so you can see there are parallelism among this instruction because the instruction on the left-hand side and the right-hand side, they can execute it in parallel, out of order, as well as the partial order within each of the dependency chain is not violated. All right, so
I didn't get why the circle 2 is 1 row behind 1.
because you only have one memory pipeline. So you can only have one instruction get into the memory pipeline each cycle.
Does it mean that if we fetch 2 instructions at the same time, the first instruction will
Get the priority.
Okay.
Yeah. All right. So that's the conventional swap. Now, looking at the exclusive OR version. All right, let's wrap up in 15 seconds.
5, 4, 3, 2, 1. Time is up. Okay, so looking at what you guys saying. Uh-oh, we need discussion, right? So now 90 seconds, go.
That part I could understand. It's 30 something depending on both. Yeah, the third instruction depends on.
All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after discussion, okay, leading toward E now. So again, right, each cycle we fetch 2 instructions. So the first cycle we have instruction 1 going in, and this one still the same as the previous example, that because we have only one memory pipeline, so only one of them gets into the memory pipeline. So the second instruction, you have to wait for the next cycle to go to the memory pipeline. But now the next cycle we fetch 2 instructions, 3 and 4. However, if you look at the dependency between 3 and 4, you will figure out that 3 is depending on 1, so it has to wait. However, it's even worse in a way that the 3 is now also depending on 2. So not only waiting for 1, but also waiting on 2. So it turns out that originally, if it's only depending on 1, you can put it here. However, because it's also depending on 2, so you can only put it here. Now, the fourth instruction is depending on the outcome of the third instruction, right? So fourth instruction can only be executed 2 cycles later. Now, the fifth one is also depending on the outcome of the fourth instruction, another 2 cycles, right? And the store instruction, depending on the outcome of 5, another 2 cycles. And for the 7th instruction, depending on the outcome of 4, it can be executed here. So that's the data flow graph you can draw out from here. And so did you see that difference? Right? Why exclusive OR swap is not a good idea? Right? So in terms of modern processor design, in terms of modern superscalar out-order processor, you have the instruction code, and you should design code that has the best instruction. The exclusive OR seems fancy, seems non-trivial, seems demonstrating that you are a smart engineer because you know how to use exclusive OR. However, in terms of this instructions, meaning that you are even 3 cycles behind the most simple 9. Why are you using this? Why are you using this? It's not a good idea. And I'm telling you, because of what? Because of modern processor design. It's out of order, it's superscalar, you have multiple pipeline functional units available for you. This one is preventing you from using fully utilized. Right? See, every instruction is in the same tree. Right? But the previous one, you have 2 perfect sequence of instructions that can be always executed in parallel. But that's not the case if you use exclusive OR. So that's not a good idea. All right, another idea that people love is linked list. So how about linked list? Alright, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Whoa. All right. Discuss. 90 seconds. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay. See. Okay. Slightly changed. So leaning toward E now. So again, right? Static instruction, dynamic instruction. This is a linked list with 3 nodes, and its branch prediction is perfect. You can imagine that these are the total of the 9 instructions that we will be executed for this piece of the code. And again, if this is a 2-issue processor, the first cycle we got 2 instructions in, and the first instruction is a load instruction, and the second instruction is an add instruction. Do they have dependency? So can we put both of them into execution? Go, right? And now, how about the third instruction? Is it can it be executed immediately after being fetched, being renamed? No, so we have to wait, right? Wait for the outcome of instruction 1. How about the fourth one? Can we put it into execution? No, because we have to wait for 1 as well, right? However, this is a load instruction, this is a branch instruction. So fortunately, they can both be being issued at the same time. Now we got a 5th instruction, it's adding x7. Are we okay to execute it when we fetch it? Yeah, right, because the second instruction is dead, right, at the time. So how about the 6th one? Are we able to execute it? No, right? Because it's depending on the value of x10, right? So then another dependency, right? So if you keep going, it's pretty similar for the rest of the instructions. And it turns out that, yeah, we do have parallelism here. However, this part is giving us trouble, right? And if you look at this part, what is that part? The pointer chasing part, right? You are loading the pointer from your next pointer, which turns out that give you a lot of troubles on that. Right? So, however, if you're just incrementing, it doesn't give you that trouble. So, does that inspire you something? If you can use an array, use the array. If you can use the array, use the array. Don't use linked list. Linked list is sometimes not a good idea. A lot of my friends working in the game industry, they say they hate linked list.
And typically, sometimes you feel like your game is buggy because they just love array. And array out of bounds, fine. I know you guys love the game. You will reload the game. You will relaunch the game anyway. Right? So, but the reason why they love array because they want short latency. And if you use linked list, I know it's more robust, but the performance really is really bad. I'm thinking about not to use some profanity words, but the performance is really bad if you use linked list, right? So that's why linked list is not a good idea. And it turns out that it will take a total of 13 cycles to issue all 9 instructions. All right, so linked list, right? Okay, so well, so far we assumed the case that we have a perfect branch predictor. However, even though you have the best branch predictor, you know, like even for perceptron, it takes time to train. Even for the global history predictor, although it works well at the end, however, in the very beginning, you are going to mispredict a lot. Right? So what if an instruction here is mispredicted? Then it turns out you have to flush instruction. However, here your instruction like instruction 8 is already ahead of 6. So what does that mean is that your instruction 8 is already changing the value of x7. So when you go back, right, the value is not going to be correct. So this process of design, if you simply out of order, it's not going to work. And another thing is I want you to think is that in which stage of your pipeline can the PC potential be checked? All right, wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay. Aha. No more distribution, huh? So definitely some discussion. Quick. Go. Just like the previous slide where it's all right, wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so after discussion, oh, more of you think it's C because you love the majority. So now at least you guys agree with 3 of them would change the next PC. So tell me, what do you think? is it possible that when we fetch instruction, that would change the next PC? No? Yes? Who think that's correct? Who think that will change the PC? When you fetch instruction, after you fetch the instruction, are you going to change the PC? Is there a case that we can potentially change the PC? Don't feel shy. Tell me. What?
I'm confused now.
You're confused? Why?
Yeah, there's no here now.
Okay, so the thing is that the next PC is presumably PC class 4, right? Branch instruction is an example that we change the next PC. So if it's an instruction, after we fetch the instruction, are we going to change in the next PC? Except for class 4. Sorry. Yeah, the next PC is by default class 4, right? Are we going to change the PC? No? Okay. How many of you took undergrad operating systems before? Okay, so do you guys remember one thing? Which memory are we interacting with? What kind of memory abstraction? The virtual memory abstraction. Right? So what if, when I fetch the instruction, there is a page fault? All right, if there is a page fault, I try to fetch the instruction, there's a page fault, who is going to deal with that? The operating system has to deal with that, right? And you have to jump your PC to the operating system code to handle that. And the detailed mechanism, next quarter 202. But now, just remember, you will have an exception handler, page fault handler to deal with that, right? And page fault handler is also a piece of code with a different PC that is not PC class 4. Okay, how about instruction decode stage? Is there any cases that would cause the situation to be not PC class 4? The what?
The decode the branch instruction.
The decode the branch instruction. Okay, but how about a regular instruction? Page fault, but that has been handled by the fetch. So after you finish fetching, you know the instruction is already in the memory, get it. So the thing is that, what if I try to run code that's not even the binary? Have you ever tried to run a Windows program on Linux or the other way around? Right, those are instructions unrecognized. Right? So then that will jump to some exception handle. Right? The exception handler is probably another piece of operating system called print, illegal binary. Right? But anyway, that would change the PC. How about the execution stage? If the instruction is already executing, are we going to change the PC? The next instruction to fetch, are we going to change that?
Yeah.
How come?
Like if we do like a divide by 0.
Okay, awesome, right? Divided by 0, overflow, underflow. We need an exception handler. Pretty much print a message, right? Not a number or something else. Right? How about memory stage? Data memory access.
Yes.
Yes? Sec fault, page fault, right? Because data memory also resides in a virtual memory abstraction. The only thing that won't cause the next PC to change is probably write back because that everything is ready. So
not just the branch, right? Even though I'm executing an instruction, there are still cases that would make the next PC go wrong. So previously we said branch prediction, even though branch prediction is perfect, there are still cases that where your PC might change, right? So what if exception occurs here, right? Like the load instruction, if I have the exception occurs here, then any instruction like this one goes ahead, or this one, like, okay, if the instruction, if the exception occurs in this load instruction, then here we go. If the add instruction has an exception, goes into the integer stage, right? Then, however, you will see that this instruction has already been written back, right? So if the exception occurs here, if there is no other thing to help you, there is no way for us to roll back. So it turns out that one thing that we have to deal with is speculative execution. So far, we ignore the fact that branch prediction is imperfect. However, in fact, whenever you are fetching instruction under the guidance of branch prediction, this instruction is called speculative. It becomes non-speculative only if the instruction is 100% certain or sure it's going to be finished. And because these instructions are speculative, we need to preserve the capability to restore the states before it's being executed to accommodate the case of branch misprediction and those exception cases that we just mentioned. So how do we fix that? So it turns out that in addition to the front end that we just mentioned, on the back end, at the very, very back end, we add a new data structure, or say a hardware structure called reorder buffer. So the basic idea of a reorder buffer is a buffer keeps track of the program order of instructions. So our front end, we fetch instructions in order. However, when we issue instructions, we make the issue out of order. So if you want to make sure that I don't mess up when if one of them gets canceled, gets mispredicted, the most important thing to do is that you still maintain the order when you present the result to outside of the world. So those results, execution results, here we have a reorder buffer that you can combine with your instruction queue, since instruction queue is the original order of your instruction. So we combine this with the instruction queue. And we add another stage called commit, which means that the outcome be realized to the rest of the world. And an instruction can only completely leave the pipeline, meaning that free up all the resources, including the order buffer entry that it occupies, until all the previous instructions of that particular instruction has finished. However, if any of them, any of the prior instructions failed to commit, meaning that all the rest after that instruction are not going to be executed. Or even though we want to execute it, they should depending on a different value. So in this way, we just clear up the entries after the failed instruction. So that's the idea of the buffer. So how does that work? Is that at the end of the pipeline, we have this reorder buffer. And what would happen is
Okay, so here I make the reorder buffer to be part of the instruction queue, and the reorder buffer I make it a circular queue structure, so I have the head and the tail. So this pieces of pipeline, let's keep going, and so you can see the head and tail they separated away. Now, when I finish the first instruction. And as you can see, right, previously, this instruction, once it finishes, it's gone. But now it's in its commit stage, meaning that we still keep this instruction and its value and its value in a physical register. And now, once the first instruction in a commit stage, right, then it means that the first instruction we have no trouble committing it because no one before it, right? So when the first instruction gets committed, that's meaning that the rest of the instruction, the second instruction can also get committed. However, here it's not finished yet, right? So and because the second one is not finished yet, all the following instructions, even though they are finished their execution, they are still in the reorder buffer. Right? However, for the first instruction, because we are done, right? So we can free up the entry and move the head to the next reorder buffer. Now, this cycle we finally commit, allow this instruction to commit. However, the third instruction is still not finished yet. Right? So even though this instruction they have been finished a long time ago, they still have to wait. Right? However, the good thing is what? The good thing is that if there is, say, there is an exception here, right, then we could just flush all the entries afterwards, and this instruction, their execution can be immediately suspended or flushed. However, previously, if you don't have a reorder buffer, this instruction is already gone way more, and this branch is already gone way further, and you are fetching more and more instructions, and it's almost impossible to recover. So if you keep going, right, now finally, after the stored instruction finishes execution, the rest of them can be committed as well, right? Then this is the execution, the diagram. However, if you just look at the time we spend to issue, the issue cycles is about the same. However, the tail, the latency of issue instruction is longer. However, this is a must to make sure that your processor can support precisely exception handling as well as handling the branch misprediction case. So this is a must. Okay, so this is reorder buffer. So again, this is still the type. Well, let's run another pieces of a code and see how good is a Superscalar processor, automotive processor plus reorder buffer for this pieces of code.
All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay. Discussion, right? Go. All right, let's wrap up in 15 seconds. Five, 4, 3, 2, 1. Time is up. Okay, so looking at what you guys think. Okay, now more of you think it's D, but still quite a lot of uncertainty here. So let me walk through this one, right? So again, first of all, one thing to remember. Adding a reorder buffer only change the back end, but not affecting the front end. In fact, the reorder buffer can bring the benefits that in the past, if you want to make sure that you can, if you want to make sure that your processor can execute correctly, you can only have one branch at the same time because you only have one branch unit. But now, before the branch is resolved, all the instructions shouldn't be fetched. However, with reorder buffer, you can just rely on your branch prediction, and since the reorder buffer is going to help you recover the mess, even though your branch prediction messed up. So you can just keep fetching as you predicted and keep issuing, no worries about anything else, right? So the front end doesn't change it. In fact, the front end can be potentially more efficient. So if we have 2 fetch widths and 2 decode widths, let's fetch 2 instructions in the first cycle. So for the first cycle, are we able to put these 2 instructions into issue? Yes, right? Because these 2 instructions, they are not depending on each other. So execute, issue them. How about the second cycle? We fetch 3 and 4. Are we able to execute them? Not the third one, right? How about the fourth one? Not either, right? Right? So 3 have to wait, 4 have to wait, right? And how about 5 and 6? Are we able to execute them immediately? So 5 is depending on the outcome of 2. Who else is it depending on?
Just wait for
It waits on the 1. Why is it waiting on the 1? It's not waiting on 1, right?
And if it's a register renaming, they will be the alias, right? So 5 can be executed. How about 6? Can we execute 6? Yes, why not, right? However, here I put it a cycle later because here I have an issue with S2. And I already issued 2 instructions here. So I have to wait a cycle later to issue the 6th instruction. However, if I make the issue with unlimited, then I can potentially put this a cycle earlier as well. Now, the 7th cycle, the next cycle, I have 7 and 8. Can I execute 7? Who is 7 depending on? 3. So is 3 ready yet? Not yet. So we have to wait, right? And it's also depending on 5, right? So turns out that it has to be this late, right? And for 8 instruction, it only depends on the value of 6, right? So turns out here is the result, right? 1, 2, 3, 4, 5, 6, 7. So the answer is probably D. Got it? All right. So for this pieces of a code, now don't be scared, right? 10,000 times, right? But this is just, if you look at instruction 1 through 4, it's the same as the previous example. So now I'm just, and previously we unrolled this loop for 2 times. Now let's do it for 10,000. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, this is what you guys think. Okay, most of you think it's B, C, or D. So why don't you go ahead and discuss with your friend to figure out what should be the right one.
Yeah, I'm pretty sure. But so that should be like a seasonal. So it's running to the
All right, let's wrap up in 15 seconds. Five, four, three. Okay. 5, 4, 3, 2, 1. Time is up. Okay, so after discussion, okay, it changes, right? And
This one has the check mark.
what?
This one has the check mark.
This one has a check mark, right? I feel like this software is always like a maze. I never know. All right. So what happened? So first of all, right? You remember? Well, we previously unrolled this for a second time, 2 times. So what if we want to unroll it? So let's keep going a little bit. Let's say like I have 9 and 10, right? Which is another load and another add. Again, the add is on another chain, right? So the add instruction can always execute, and the load instruction is depending on this one, right? Sorry, the ninth instruction is depending on the outcome of x10, which comes from the 6, and this is also depending on the outcome of 6. And 11 and 12 is depending on, how come I have this box here? It's so confusing. All right, so 11 and 12, 11 is depending on the load result of instruction 9, right? And 12 is depending on the outcome of 10, right? So one thing we learned is that if you observing the graph, you can imagine the critical path of this execution is depending on this part. You can see a lot of this in your graph. You can see a lot of this. It's just a replication of this, right? So if I keep having others, right, you can imagine it just keep replicating this part. So how many cycles it takes to execute this part? So if we look at this, 1, 2, 3, 4, 5. And how many instructions? Okay, not 5. So, okay, 1, 2, 3. Yeah, I confuse myself. I'm also getting myself confused. Okay, 1, 2, 3. Right here is the loop 1, and now nice. Let's say like this is the beginning of the next. We can consider this as the beginning of the next iteration, right? 1, 2, 3. That's another one, right? And 13 comes from here. So you can see there is a 3 cycle gap for every iteration,
And how many instructions are there in each iteration? 4, right? So 3/4, 3 cycles for every 4 instructions. What does that mean? Your cycles per instruction is 0.75.
I'm a bit confused because the question is asking the CPI.
Uh-huh.
And I thought the CPI is cycle for instructions, which means the completion cycle, not the.
Well, but even though for the completion cycle, you just add a few ANs.
And what I'm confusing right now is since we have the ROB, we should wait for the commit stage.
Right.
Yes.
But here I'm assuming that you have a limited ROB, and we have to wait for it to commit, right? But as I said, that only adds like a total of 10 or whatever at the very end. Agree with that? So if you have some, that's why I'm saying about 10,000. If I have sufficient amount of instructions, then on average it's only 0.6. Do you agree with that? Question?
Question says it takes 3 cycles to execute our instruction.
Uh-huh.
I think we need to.
That's no 3 cycles because you have 3 cycles. It's still a memory instruction. It's real like that. That was the same as the previous example. You have AR, AQ, and okay. All right. So here, one thing you've learned is that we have finally achieved CPI less than. That's the biggest point. However, there are still instructions on the critical path that prevent us from getting better, right? But looking at this processor, you have issue with 2, and but turns out that you can only if you have issue with 2, right? Theoretically, your CPI is 0.5. That's the peak. However, now we only have 0.75. So there are still some lessons or something that we have to deal with here. But and that's what we are going to talk about in the next lecture. But before that, let's look at how similar are those pipelines or this out-of-order execution model that we learned so far and coherent. How are they coherent with the modern processor pipeline? So I'm not sure how many of you are interested about those hardware website that talks about the most fancy processor design. They typically will show graphs like this. Like this is a pattern for pipeline the high-level architectural design. And previously, you probably don't even want to dig into the detail. But now, if you look at this, right? Hey, BTB, what is that? Branch target buffer. Yeah, I know what is that, right? TOB. Prefetcher. Instruction decoder. Right? Trace cache. Well, you don't know this. I should have another something. All right, and another thing that is interesting is that for Pentium-4 processor, because it's an x86 processor, and x86 processor is a CISC architecture, but now the backend pipeline of Intel processors are low risk based, like the pipeline processor design. So their decode stage would actually translate their x86 instructions into the micro up. So they have a microcode ROM and a micro up queue, which is the real instruction that will be executed in the rest of the pipeline. Yes.
Why do they do the translation? Why not just keep it on there?
Well, because the x86 instruction itself is very hard to parallelize or very hard to deal with. Yeah. If I want to discuss this, it will take weeks. But that's why sometimes you have the assembly class, assembly language, right? But to be short, those x86 instructions, they are too complicated to make an efficient pipeline. Okay,
So register renaming. You know what it is doing, right? Now, integer floating point pipeline memory queue. Right? Isn't that similar to what you just learned? Right? And they have multiple register file bypass network for two of the LU, slow LU, address generation unit for one for load, one for store, and floating point unit. And finally, L2 cache, right? L1 cache. Yes.
What is the slow LU?
Oh, slow LU. There are okay. That's a good thing to ask. The thing is that again, complex instructions, right? In x86, there are some complex instructions that needs a slower LU to execute. Yeah, x86 is not.
I thought you said everything
think
is
that's the
very
base plus the offsets multiplies 4.
That I'm not sure to be honest. Yeah, but I would say some legacy. What?
Area can follow a cell's expression in seeds.
Okay.
That the expression can be calculated to the CPU.
Okay.
So, wait. I thought you said everything was translated.
They will be translated, but not all of them could be translated into fast LU operations. All right. All right. So that's pendant 4. And this is the later Intel Skylake, right? You can still read it, right? Like branch prediction unit, L1 cache, legacy decode pipeline, right? 5 micro-ops per cycle, decoded iCache, right? Instruction decode queue, register renaming, scheduler, which is the issue stage, right? And they have 1 pipeline, 2 pipeline, 4 pipeline, right? And also low story queue, right? And data cache, L2 cache. Understand almost everything, right? And it has 4 issue integer pipeline and 4 issue memory pipeline. Okay. Sandy bridge, later one. Again, instruction cache, branch prediction, scheduler, and AMD processor, still the same, right? Perception prediction, micro-op cache, micro-op instruction queue, decode stage, instruction queue, instruction cache, right? Integer rename, floating point renaming, right? Scheduler, register file, 4 issue floating point pipeline, 6 issue integer pipeline. What a magic! Now you understand everything. Not everything, but at least you can read it, right? This is not a completely innocent figure for you anymore, right? You know what the spec is talking about, right? That's the reason why you won this class, right? So again, putting it all together. Now, so again, we are so like linguist, right? Code like linguist. But you know, like even for the current pipeline or the pipeline we just demonstrated, there are still crummy software code like the linguist. In a way that the critical path is completely depending on the memory dependency chain, and turns out that we are always having the case that we are having the instruction level parallelism that is very low, meaning that the same cycle you can only execute very limited number of instructions, and because of the data dependency. And it turns out that there are slots that we cannot fully utilize the reach issue with your processors. So we will talk about a demo later in the beginning of the next lecture. But the thing is that now, if you have a processor with multiple pipelines, and if you want the performance to be better, you have to make your software or say make your processor being available to execute and issue as many instructions as possible. And one of the good examples that we just demonstrated is that for the swap function,
if you have the trivial naive implementation, you can execute two sequence of instructions in parallel. However, if you have the exclusive OR version, that's not possible. And the reason why the exclusive OR version is underperforming the other version is just because the ILP, instruction level parallelism, is bad. So, however, if you do have this kind of code, how can you still improve the overall performance or processing utilization? That's the topic that we are going to talk about in the next lecture, which is next week. And but because we haven't got a reading quiz done, so I'm not going to talk about that topic. However, there are a few announcements that we will I have to let you know. So first of all, assignment 3 due this Wednesday, and final exam. I didn't receive any complaint email within the last 48 hours. So I would say I will take the final exam online, and there is a reason why I'm doing this. And I don't want to create panic within the class, but I do see, and some of you might heard a lot of cases, or a few of you told me that, well, a friend of my friend recently tested for COVID or something, right? So, and I do see there is a chance that the COVID-19 case is going to surge again, but hopefully not too much after the holiday season. And I didn't cancel the lecture in person is because see how many of you are here, right? So that's not really an issue, right? But for final exam, if I have to put everybody in the same room, I don't think that's not a concern. So I'm not going to do the final exam anymore. And there's a reason for that. And here are two figures that I grabbed from the dashboard in two different schools. The up one is UC San Diego, and you can see the blue one is the case of a student got infected, steadily increase, right? And this bottom one is UCR, right? Up here, slightly up, right? So I don't think the curve is encouraging at this moment. So final exam will be online, no choice. You have no. I think it's safe to make it online, and that's my final decision. And sorry for those of you who think the final exam will be in person, but given the COVID-19 situation, I still don't feel comfortable that we should make the final exam online. Sorry, in person. Reading quiz due next Monday. Project, no extension. Try to get it done after the Thanksgiving. Other than that, enjoy the rest of the day. Enjoy the rest of the week. I will see you next week.